Hi ladies and gentlemen, today we are going to start section 2.2 Axioms, Interpretations and Properties of Probabilities. In this part we will talk about the objective of probability. We are going to talk about the basic properties or axioms of probabilities. We will discuss about the other properties of probability and we are going to prove them. Here is your homework for this part. Also you can have a look at examples in section 2.2, examples 2.11 to 2.14, and it's an additional exercise. You remember that we talked about the probability as a numerical measure of the likelihood that an event will occur, and we talked about experiment as any action or process that its outcome is not known in advance, and also we talked about sample space as a set of all the possible outcomes of the experiments, and event is any subset of a sample space. What is the object of probability? Suppose an experiment with a sample space S. The objective of probability is to assign to each event A a number PA called the probability of event A, which will give a precise measure of the chance that event A will occur. So in short, PA is the probability of event A, a precise numerical measure that gives us the chance or likelihood that event A will occur. Before talking about axioms of probability, now at first we should know about the axiom. What is the definition of axiom? In mathematics, an axiom is a result that is accepted to be true without the need for proof. So all of us must accept that the axioms of probability are true without any need to prove. But what are the axioms of probability? Number one, probability is non-negative. It means for any event A, the probability is 0 or larger or greater than 0. Probability is not negative, it's non-negative. It means probability is 0 or greater than 0. Number two, for the sample space S, the probability of S is 1. Sample space is a certain event. It means for a certain event, the probability is 1 or 100%. But why the sample space is a certain event? Before we talked about happening of an event. When you, for example, roll a dice, the sample space is 1, 2, 3, 4, 5, 6. And suppose we have, for example, 2 or 3 events or subsets from S. 1, 2, for example, 6, and 1, 4, and 6. Anytime you roll a dice, the result is or the outcome is always in S. But it's not always in A, it's not always in B, it's not always in C. For example, if I roll a dice and I observe 4, then 4 is not in A, 4 is not in B, 4 is in C, and 4 is in S. So A has not happened, B has not happened, C has happened, and S has happened. What if I roll a dice and I observe 5? 5 is not in A, 5 doesn't belong to B, sorry, a 5 is not in C, but 5 is in S. So A has not happened, B has not happened, C has not happened, but again S has happened. So because S have the all possible outcomes, it means anytime you roll a dice, S will be S will happen, but for other events, no. Sometimes they happen, sometimes sometimes they don't happen. But for S is a certain event. Certain event. So for any certain event or for a sample space, the probability of S is 1. You can see here. Number 3. If A1, A2, A3 is an infinite collection of disjoint event. Please note that disjoint event. You know about the disjoint. Disjoints A and B in this diagram are disjoint because they don't have any outcome in common, or the intersection of A and B is empty. So if we have an infinite collection of disjoint event, the probability of the union of them, it means the probability of A1 union A2 union A3 union A4 and so on, is the sum of the probability of A1, A2, A3, A4 and etc. For it means the probability of A1 union A2 union A3 and etc. is the probability of A1 plus probability A2 plus probability A3 and so on. But if AI are disjoint events, now we want to talk about more properties about probability, but in the form of some propositions. But what's the meaning of proposition? A mathematical statement that is either true or false. For example, 3 greater than 4 is a mathematical statement, but it's not correct. 4 greater than 3 is a mathematical statement, but it's correct. So, a mathematical statement that is either true or false, but note that in this course, all the proposition will be true. and can be proven true. And the proposition often follow from definitions or axioms. So we can prove these propositions about the probability by using the axioms that I told you about them before. Number 1, the probability of impossible event or empty event or null event is always 0. So the probability of null event or impossible event is 0. But how we can prove this proposition? By using axiom 3, we can prove this proposition. In axiom 3, we have that the probability of A1, we can write that the probability of A1 union A2 union A3 is the probability of A1 plus A2 plus A3 and so on. All of us in mathematics, from mathematics, we know that the union of two or more empty sets is empty, and the intersection of two or more than two empty sets is empty. This one shows that the empty sets are disjoint because the intersection of them is empty. So because we have this assumption, we can use axiom 3. Now we consider that, or we suppose that A1 is empty, A2 is empty, A3 is empty, and so on. So the union of A1, A2, A3, A4, and etc. is empty. And here we consider that A1 is empty, A2 is empty, A3 is empty. So we can write that the probability of empty is the probability of empty plus the probability of empty null plus the probability of empty null plus etc. So this equation is valid if and only if the probability of null event is 0, because only for 0 we can write that the 0 is the sum of zeros, not for any other number. So we prove that the probability of the null event or the empty event or the possible event is always 0. In the second part of this proposition, we have this in turn implies that the property contained in axiom 3 is valid for a finite collection of events. But what is the meaning of this? It means if A1, A2, A3, K is a finite collection of disjoint event, again disjoint event, then we can write that the probability of A1 union A2 union A3 2 union AK is the probability of A1 plus probability of A2 plus probability of A3 2 plus probability of AK. But how we can prove this? Again, by using axiom 3 and the first part of proposition 1, we can prove it easily. So we have the probability of A1 plus probability of A2 plus probability of AK plus probability of AK plus 1 plus the probability of AK plus 2 and etc. is the probability of A1 union A2 union AK union AK plus 1 union AK plus 2 and etc. Now suppose from AK, it means AK plus 1, AK plus 2, AK plus 3, and so on. We have all of these events as empty events. It means AK plus 1 is null, AK plus 2 is null, AK plus 3 is null, and so on. So for this part, it means from here to the end we have union null, 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 and also in this line null, null. So what happened? It means that we have the probability of A1 plus probability of A2 plus probability of AK is equal to probability of A1 union A2 union AK. Because the union of any set with an empty set is that set, the union of A and empty is A, and here the probability of empty or null is 0. Here is 0. It means plus 0 plus 0 plus 0. So by considering these events AK plus 1, AK plus 2 to the end, we could prove this equation. Proposition 2. For any event A, the probability of A is 1 minus the probability of A prime. It's a very useful equation because sometimes using A prime in calculation is easier than using A. But how we can prove this proposition? From mathematics, we know that A prime union A is S, and A prime union, A prime, oh, again, A prime union A is sample space, and A prime intersection A is empty. So A and A prime are disjoint. Again, by using axiom 3 for a finite collection of events, we can write that the probability, because there are disjoint, we can write the probability of A prime union A is the probability of A plus the probability of A prime. This part is S, so the probability of S is the probability of A plus probability A prime. From axiom 2, we know that the probability of S is 1. So 1 is probability A plus probability A prime. So the probability of A is 1 minus probability of A prime. Proposition 3. For any event A, the probability of A is 1 or less than 1. It means the maximum value of probability is 1 or 100%. The probability of A is 1 or less than 1. But how we can prove this proposition? From the last proposition, we obtained that the probability A plus probability A prime is 1. From axiom 1, we know that for any event, the probability is non-negative. It means the probability of A and the probability of A prime are 0 or positive. So the probability of A plus the probability of A prime is equal or bigger than the probability of A. Why? Because if you add a positive value to another positive value, it's always greater than the original value of P, the probability of A, because this part can be 0 or can be greater than 0. It means we add a positive value to the probability of A. So the result is greater than the probability of A or equal to the probability of A. Again, in this part, from here, it's 1. The probability A plus probability A prime is 1. So we prove that the probability of A is 1 or less than 1.